Okay, so here we are on the verge of defining our first logic language called propositional logic, and this will give us some insights into the algorithms that we use for computing proofs or computing derivations. So, propositional logic often we will use the acronym PL to stand for that, propositional logic, or it is also called propositional calculus, is the simplest of logic languages. The atomic sentence, the smallest sentence, remember that an atomic sentence is a sentence without any connectives. So, the other sentences are the sentences, for example, alpha implies beta or alpha or not beta. So, they have logical connectives essentially. An atomic sentence is a sentence in which there are no connectives, and the atomic sentence in propositional logic is a symbol, just anything, for example, the symbol P, and we say P is a sentence. What does it mean that P is a sentence? That in principle, if you were to give truth values, then P could be given a truth value of true or false essentially. And it stands for some sentence. We have not, when you are talking about logic, we do not need to specify what it stands for, but as we see examples, when you are talking of a specific domain, then you may have certain domain in mind, and then of course, symbols will stand for specific things, and that we will see as we get along. So, a symbol can stand for any sentence. So, here are some examples that I have written. All men are mortal. We saw that was part of the syllogism. But as far as propositional logic is concerned, it is just a sentence. We could call it P or Q or R or anything, it does not matter essentially. Then any of the other sentences that I have written here, the moon is made of green cheese. You may not believe it, but it is a sentence, which means it can be either true or it can be false. So, most of us of course, will believe that it is false, because by now we know that it is not made of green cheese. We have got astronauts landing on the moon and stuff like that. Then also there are the following two sentences: the earth is round, the earth is flat. Of course, only one of them will be true, and we know it is the first one, but both are sentences essentially, and we could have used a symbol to stand for that. Then of course, we have two interesting sentences, which is the tomato is a vegetable, the tomato is a fruit. Are they true? Are they false? I will leave you to think about them. It really depends on how you perceive the world essentially. Okay. You may think of the tomato as a vegetable because you put it in, let us say, making sambar or something like that, but you can also think of it as a fruit, because nobody stops you from just chopping it and eating it. So, it is up to you, but these are sentences essentially, and the truth value of course will have to be defined in some this thing. The sentence is atomic or indivisible. We do not look inside the sentence. We have said, if you take the first example, our favorite sentence, that all men are mortal, and we are saying this is a proposition or this is a sentence. Between you and me, we know what we are talking about, because we understand English, and we have an understanding of what is a man and what is mortality and so on. But in propositional logic, we do not peer inside it essentially. We do not say that, oh, it is talking about men, and that it is talking about all men, and then it is talking about some property that all men have, which is that they are mortal. We do not break it down in further. We simply say this is a sentence P, and you tell me whether it is true or not, and then I will do something with it. Whatever logical reasoning one can do, one will do with that essentially. Now, obviously, you will think that this is very restrictive, is that if you do not even know what you are talking about, and how can you, for example, infer from this that if Socrates is man, then Socrates must be mortal, and the fact is that in propositional logic you cannot essentially. We need a more expressive logic, which is called first order logic, which is what we will do after we have done with propositional logic, and we will show that we need something more expressive then propositional logic or a logic of sentences to be able to talk about things in a domain. So, elements in a domain. So, man is a set of is from the set of humans, for example, and so on. But in propositional logic, the sentences are atomic. We do not look inside it essentially. We just treat it as a unit which cannot be broken down any further. Logic itself, as we have been trying to say, is not concerned with meaning. What does it stand for? We do not care. You just tell us some relations between things, and we will tell you that yes. So, I mean, we have seen this example, right? Modus ponens is our favorite, that if you say P and if you say P implies Q, then we can infer Q. What does P stand for? What does Q stand for? Logic is not bothered about that essentially. It is not concerned with meaning. It is concerned with valid patterns of reasoning, and this is a valid pattern essentially. Meaning lies in the mind of the beholder. I mean, if I am going to say that P stands for that the earth is round, then it is in my head essentially. As far as logic is concerned, P is just a sentence. Likewise, a sentence is or a proposition is in principle true or false. We have been saying that, and again this truth value is externally supplied essentially. I mean, there is nothing in logic which will tell you whether the sentence is true or not. Somebody has to tell you that this sentence is true or not. Again, that is the reason why valid forms of reasoning say that if P is true and P implies Q is true, if you tell me that P is true and if you tell me that P implies Q is true, then because my system is sound, I can tell you then that Q is true. But logic itself is not even concerned with truth values. What it says is that if you give me these two formulas, P and P implies Q of these two sentences, then I can add this to your knowledge base. The fact that the knowledge base is a set of true statements and that the conclusion must be true and all is the notion that we have been talked about. I think to a fair extent now, the notion of soundness and completeness and stuff like that. But the basic unit of a propositional logic is a set of basically a proposition, which is a sentence which is atomic in nature, in the sense that you do not look inside what the sentence is saying. So, we had said that a formal language is a language in the sense that it is a set of sentences. So, you would have studied, for example, if you have done a course on formal languages, that there are regular languages, there are context free languages and so on and so forth. But basically all of them are set of sentences which are defined using some simple rules. They do not even have to be defined using some rules. You can actually explicitly say that this is a set of sentences that I am dealing with. But basically in a formal language, there is a set of sentences that we are talking about. So, let us see what are the set of sentences that we can talk about in propositional logic, and that is what we are talking about, the syntax. How can we construct sentences? How can we construct more sentences given simple atomic sentences like P, Q and so on? So, every time you build a logic, you will have a constant or a logical part, which is to do with the logical connectives and the logical reasoning. Logical reasoning is based on the meaning of logical connectives, right. So, when you say the logical part of the vocabulary, that means what are the connectives that we are using here. If you are writing programs to do reasoning or inferences or deduction, then of course, you would have certain domain in mind, and then you would choose that okay, I need so many variables, I need P, Q, R and I need something. We will see an example as we go along. So, the constant of the logical part, which is there in practically all languages that have been devised, are the symbols that we have already seen, which is the symbol. By now, we have got so used to calling them by their names that we might as well do it here, and or negation or implication. But as far as the syntax is concerned, there is no association with the truth table that we associate with AND essentially. As far as syntax is concerned, this is just a connective, and we know that of course, that this is a unary connective and the others are binary connectives, which means a unary connective takes one sentence and gives you a new sentence. Binary connectives take two sentences and give you a new sentence, and these are just connectives that are going to be useful for us. And with advanced knowledge or hindsight, since we have been talking about truth tables, we will use the same names, that we will call this first one and the second one, or the third one not, and the fourth one implication. But that is because we have already kind of figured out that is what we would want to mean by these connectives, or that is how we would like to define the semantics of those connectives. In reality, there is no connection between the truth table and these connectives. It is just that when we define the semantics of propositional logic, we will see that of course, we will define it based on the connective. So, it is a very subtle difference, but you must keep it in mind that the connective symbol that you use, which is this inverted V or the V or these symbols, they are independent of the meaning of those truth tables that we are going to associate them. Of course, we are going to associate them with that, but they stand by themselves. We could have just used a different set of symbols in the truth tables and a different set here, and then establish the association. But it makes it simpler for us to think of them as the same thing. But that distinction is subtle, and you must always keep it in mind essentially. Then of course, there are these symbols that we use for brackets, and we are familiar with this sort of stuff by now, and the constant symbols. In two valued logic, there are two constant symbols. The first one is called the bottom, and the second one, which looks like a T, is called the top essentially. These are sentences that when we define the semantics of the language, what do we mean by we will define the semantics, is that when we will define as to, you tell me you give me any compound sentence, we know what compound sentences are by now, and we will decide what their truth value is. So, for constant symbols, and that is why they are called constant symbols, their truth value is false and true respectively. It is like when you do algebra with numbers, which is also what you are doing with logic, is that if you have a constant symbol like 0, then you know that it stands for the number 0 essentially. Again, there is a distinction between the number 0 and the symbol 0 essentially. But if you have a symbol called x, which is a variable, then it could stand for any number essentially. So, likewise, the sentences in our logic can stand for any, can have any truth value except the constant symbols, which will always have the same truth value, and bottom will have false and top will have true essentially. And it is only in our heads that when we say that it is false, this is what we mean, which means it is false in the real world. But otherwise, they are just a pair of there is a small set to which we will map all sentences. So, some sentences we will map to false, some sentences will map to true, and the interpretation is in our heads essentially. So, that was a constant of the logical part of the vocabulary, which is there in all languages. Even in the more expressive languages that we see, we will see these things. And there is a variable of the domain specific part, that if you are solving a particular problem, if you are encoding it in logic and trying to derive a proof, then of course, we will have to choose certain set of symbols, and these are the set of symbols which we will use this P in a different font to stand for this set of propositions, and it is a countable set of propositions. Basically, you can choose any number, and there is no limit on how many you can choose, but you should be able to enumerate them. that this is the first symbol, this is the second symbol, this is the third symbol and so on. So, for example, P1, P2, P3, or more often than not we use different symbols, because we have certain things in mind. So, PQR and so on and so forth. So, this is the simple the alphabet of propositional logic. I should have written this somewhere. So, this is the alphabet of this language. Now, we are talking about sentences. Remember that logic is concerned with sentences, and sentences are what? Sentences are something which are either true or which are false, essentially. In terms of formal languages, we say that these are formulas or well formed formulas, which mean that they are formed using the set of rules that we are going to describe just now. That is how you can form more sentences. You start with a set of atomic sentences, which are from this set P that we have said, that every proposition symbol is a formula. So, we will use the term formula and sentence interchangeably. When we move to the next logic, which is first order logic, we will see that there is again a small subtle difference between a formula and a sentence. Whenever we say formulas, we mean well formed formulas. So, formula is just a short form for saying well formed formula. And in propositional logic and in all logics, in fact, we have atomic formulas, and in case of propositional logic, the atomic formulas are the set P, that is you start with by choosing a set of propositions. And so, this kind of rule says that if alpha belongs to this set of symbols that we have chosen, then we can say that alpha is a formula or it belongs to the set of formulas. So, atomic formulas are also formulas, but there are other formulas which are not atomic, and we already have an idea of how what is happening there. You can use a unary connective to construct a formula. If alpha is a formula, which is a way of saying that alpha belongs to this set F, then not alpha is also a formula. So, we are defining this language, we are defining what is a set of sentences that we are talking about. So, first we chose a set of proposition symbols, and then we are now adding logical connectives to say that okay, these are the other sentences that you can construct. We have seen binary connectives also. So, if this is some binary connective, it can stand for, it is like a variable connective, it can stand for and or the ones that we have seen, Schaeffer stroke, Pierce arrow and so on. Sorry, not this, that is a unary connective. So, if that is a binary connective, and if you give me one formula, two formulas, which two somethings which are formulas, or alpha is a formula and beta is a formula, then we take the connective, we put two brackets around it, and we say okay, this is a new formula, and that is how we can construct more and more formula. And as we do when we give definition of sets mathematically. So, the set of formulas F is the smallest set satisfying this above. What do you mean by the smallest set satisfying above? Is that you can only construct formulas using this set of rules, and there is nothing else that you can do essentially. So, for example, you cannot say that alpha you cannot say this is not true. Alpha negation sign beta is not a formula. So, formulas are only those that can be constructed using these rules. So, for example, alpha and or beta does not belong to the set of F. That is not a formula. You can't put two logical connectives in between two these things. So, only what you can do is what we have done here, and that is what we mean by saying that it is the smallest set satisfying the above essentially. So, a note on Frege's propositional calculus. when we say that his calculus is propositional, we are not saying that the axioms are made of atomic formulas. We are not saying that an axiom, for example, then 2 has constituents alpha, beta, gamma. We are not saying that they are atomic formulas essentially. Those axioms simply say that these are variables essentially. You plug in anything for alpha and you plug in anything for beta, and for example, you can say that alpha is equal to P implies Q. That is perfectly valid, it is allowed. Then if beta is something else, so you plug in those things and it will still be a tautology essentially. So, for example, you can say beta is equal to not Q or R, and if I say gamma equal to P or Q. Okay, I have just written some random statements here. This alpha, beta and gamma are variables we said. You can plug in anything. You can plug in these 3 values for this and you will find that this is still a tautology. So, when we say it's his language is the Frege's calculus is propositional, we are not saying that alpha, beta and gamma are atomic propositions. Rather, we are saying that the atomic sentences in the logic are those that we are not going to peer into. That is what we said, right, that when you say P stands for all men are mortal, then that is it essentially. You can't say, oh, it is talking about men, it is talking about mortality, it is talking about all men, we can't do all that essentially. So, the atomic sentences come from this set P, that is what we are saying when we say that this is propositional calculus. But the rules do not apply only to atomic sentences, as we can see in this example here. You can plug in any alpha can be any sentence in this language, beta can be any sentence in this language and gamma can be any sentence in this language and it will still work. So, as I was saying, alpha, beta and gamma could well have been compound sentences, that is what we did here. From some more expressive language, it does not even have to be propositional language, it could have been first order logic or any other logic, and these axioms would still be axioms, they would still be true essentially. So, that is what we meant by saying that this is propositional in nature. So, we have defined the language of propositional calculus, we have defined the syntax and what we have seen is that how to form a set of well formed sentences essentially. And next we will talk about semantics essentially. So, we will come back after a break to talk about this. Just go over the definition of the syntax. Syntax is essentially what you write down on paper and what are the symbols you use and what combination of symbols is called a sentence or a well formed formula, and we have defined that set of well formed formula. Now, we will talk about semantics essentially, but we will do that after a break in the next video essentially. So, do take a break.